So today's seminar will be fully online, but I hope that it will not be a huge problem. This time I want to expand our topic. We worked hugely on phonons before. We created phonon DOS. We now know how to calculate a phonon dispersion. We know how to get such things like Kohn anomalies. And now we are going further to electron-phonon interactions. So why these interactions are so important? Because two main electrical processes as resistivity and superconductivity, they both connected to electron-phonon interactions. So like resistivity, it's obvious, electron goes through this lattice. We have this lattice vibrations, phonons, and then it interacts with it in some way, with its energy, the lattice hits, and we get this resistivity. Superconductivity is more complex thing. So we have this Cooper pairs created via in a Bardeen-Cooper-Schiffer theory. Cooper pairs, they are created by electron-phonon interactions. So we have one electron which disturbs neighboring ions, so it interacts with phonons in some way. Then this perturbation, it goes through the crystal, and then it interacts with other electron. And in this case, we can, at very, very low temperature, we can, below the critical superconducting temperature, we can this Cooper pair formation. So these electrons can bond into a Cooper pair via this electron-phonon electron interaction. How we will see it on density of states. So it's like schematic thing. That for metal, our density of states, it should be in this schematic spherical example in vacuum. So we see that density of state is constant, but when this metal goes into superconductive state, we get these two peaks near Fermi level. As I understand, Fermi level should be somewhere here in the center. And then we have this superconductive gap. So superconductivity opens some gap, some small gap, and on both sides, if you are looking on a density of states, we will see these peaks, this anomalies. It means that we have really a lot of these electrons, this electron Cooper pairs, which have the same energy. Yeah, and they are very they have super high mobility. It's like in 2 words about mechanism of it. And what about mathematics? How we can calculate all these mechanisms? We should add to our Hamiltonian just one part, electron-phonon interactions. But the main problems are with how to calculate this part. So if we will expand our Hamiltonian last term and part of this term, we have worked only with this part, with electrons. There was some ions, but doesn't matter. So we worked only with this part. So we calculated this eigenvalues, energy of bands, of electronic bands, and we created that band structure plots. We created Fermi surface plots, density of states. Then we have added another part, phonons, and for last 3 or 4, I think 3 laboratory works, we have calculated this phonon interactions. And now we improved this Hamiltonian, and we have added electron and phonon interactions. So you see this creation and annihilation operators. They are for electrons, C, and A for phonons. They are both here, and we also see this Q vector, this propagation vector, which we used in phonons. So here it's by default in phonons. And here we see that electrons should in some way interact with phonons. And we have this matrix. So our calculations, which we will make today, they will be dedicated to the problem how to calculate this matrix. So this is electron-phonon interaction matrix. It shows like coupling strengths between electrons and phonons, and it can be calculated in some energy units like Rydbergs or electron volts. So our and here is some number of here is some the density of states at Fermi level. So our goal is to get this this matrix of this coupling. Why? Because we then can get a lot of properties, a lot of superconducting properties from this matrix. So we have this electron-phonon components. I used different papers for this. So that's why here B, so here A, and here we have B, but it's the same Hamiltonian, electron-phonon Hamiltonian. So we have this Hamiltonian. We had to get this matrix, this G matrix. Да, Igoryan.
Oh, sorry. I'm sorry to interrupt you. Was just a general question. In the BCS classical formulation of superconductivity in the Hamiltonian, this coupling matrix between electrons and phonons, it's actually simplified to a constant because this is the mean field approach. As far as I remember, the classical BCS formulation, right? And
we can simplify it to lambda constant. You mean the constant?
Yeah, exactly. Yeah, that was my question. So in the DFT, these calculations, does it also get reduced to this?
No, we can. You see here we can iteratively solve this equation, and we take it from the perturbated Consham potential. So we have this Consham potential, our usual potential. Then we made some perturbations of this potential, and then we apply it, and then we made some operations with it, and then we get these coefficients of this matrix. But then from the matrix, yeah, we get some constants, and so I showed a few things here which we will calculate, and here we have this electron coupling constant. I think this is the constant you mean, because it's
yes.
Yeah, because it's easier to work with this constant, yeah, and easier to characterize something than with infinite matrix of this of this coefficients. Okay, not infinite, but it can go. It depends on our system. It can be really huge. Yeah, we will simplify it. So what things we can calculate if we will have this electron-phonon matrix, electron-phonon matrix. So we can get a spectral function. So we can see at which energy or at which at which frequency we have the highest electron-phonon interactions. Then we can get this electron-phonon coupling constant, and with this so we can simplify our goal. Our goal is to get critical temperature. Also, by calculating this critical temperature, we will calculate all this stuff. We will calculate spectral function, and we will build this spectral function. We will get this electron-phonon coupling constant lambda, and how it is simplified inside our code. So we get this matrix, then we get then we have spectral function and lambda in so huge expressions, but we can apply this thing which calls phonon line width. It's some analogous of our phonon dispersion curves, but for electron-phonon interactions. And then with this phonon line width, we will have files with phonon line width. With this phonon line width, we can simplify this expression. So for spectral function, you see we just took all this huge stuff into one phonon line width things. And then we can recalculate this constant also with phonon line width. And then we have its Macmillan formula of critical temperature. It is also some simplifications. So we don't have the general formula for critical temperature for all cases, but we have Macmillan and also Allen, they calculated, they created this formula for some cases with so for some simplified cases. They created this formula. It have even empirical coefficient. We can change it. We don't know this coefficient. We just know its range. So it's like column screening. Yeah, and we know its range, and we can see the range of critical temperature for some material. And for this critical temperature, yeah, we had to get lambda, this constant electron constant. We had to have omega, this omega, and it is connected to our spectral function. So this omega calculated by spectral function. But in the ground of all this thing, we have this electron-phonon matrix. From this matrix, we get spectral function, electron coupling constant. From spectral function, we integrate the spectral function, we get this omega, like omega critical, yeah, and then we can calculate, we can estimate, even not calculate, but we can estimate critical temperature. And I will send you these papers. They're really brilliant, but they like 64 pages each. Then how it will be implemented in our algorithm. So each step is in algorithm. First step is relaxation by default. Then we had to make two sets of self-consistent calculations. We made only one set, but here we had to make two sets of self-consistent calculations. So one set is to calculate this spectral function coefficients. So it's not like calculate the coefficients. It will be this output of self-consistent run will be presented in the way which can be read by other routine in Quantum Espresso. As I understand, it was done because this is a rather new function, this electron-phonon, and it goes from maybe 5 or 6 version of Quantum Espresso, and it was added like it was added as some additional models to the program. So we have made self-consistent calculations with very dense K-mesh to compute this, to present it in the form of the spectral function, which will be written in other steps. Then we can make calculation with lower K-mesh density, but also with high K-mesh density. Why? Because why we do these two sets of calculations? Because time of calculations, time and amount of researches, it really hugely depends on this K-mesh density. And if we have, but for spectral function, we need really very dense K-mesh. But with this dense K-mesh, it's not obvious that we can make the calculation because the time will go to infinite. That's why we make these two sets of calculations. One with super dense and another with dense but not so dense to proceed for all other steps. So then we had to take the file, the output file from here, output files from here to phonon folder. I call it now Electron-phonon folder. You can find it in lab 17 folder. Here we will calculate phonons, so our phonons from previous labs, and this electron-phonon coefficients. So the coefficients, these coefficients of this matrix. Then but we will get them in a reciprocal form. We had to make Fourier transform with Q to R. We will get this interatomic force constants and real form of electron-phonon matrix. Then with all this stuff, we will go to another step, to dynamical matrix. So we had to calculate dynamical matrix for phonon frequencies. And also we have to calculate this phonon line width. So this thing we will get from this step, this phonon line width. Then we are going to calculate phonon dose and this spectral function. You see, they are this phonon line width, it's some kind of analogous of phonon dispersion, but for electron-phonon coefficients. And spectral function in some way it is analogous of phonon density of states. That's why they are combined in these routines. So phonon frequencies, phonon dispersion, and this phonon line width, they are calculated by one calculation, and by another calculation we can get this phonon dose and this spectral function. And then we have this, if we successfully passed all the steps. Yesterday and the day before yesterday, I tried to take it, and it took maybe 6 hours for me to get the right coefficients to check for all bugs and to make today this calculation clear because I really don't like electron-phonon calculations. It takes a lot of steps. On each step, you can have some error. On each step, something can go wrong. And this example is very easy. It's just plumbum lead. Yeah, it's only one atom in unit cell. I took it from so it's like example in Quantum Espresso. It's like example in Quantum Espresso folder in the program. But for real calculation, you can expect problems at each of these steps. And the guys who are making the real calculations, I mean Mikhailo or Igor, maybe you noticed it, yeah, that it's not so easy to calculate the real system because you have to add a lot of things. Then you see that it don't work as you think, as you want, and you can expect a lot of problems at each step. Okay, we can very accurately made these calculations step by step. Yeah, Igor, I see your hand. By the way, you can don't raise the hand. You can just say if you want to say something.
Okay. I have another theoretical question about this spectral function. Can we say this spectral function represents the spectrum of electrons, of phonons, or of bosons? Is it a one particle Oh no, I see. It's not a one particle spectral function. But
not
how
one particle.
shall we interpret it?
It's not one particle spectral function. I interpret it as analogous of density of states, but for this
For those collective excitations, let's say.
Yes. So we have phonons, phonon dispersion. We have density of states. We have this excitation electron-phonons matrix, which creates this phonon line widths, and then we make some kind of DOS calculation, because you see it is really it all looks almost like DOS, because in DOS we also have this function. Yeah, it's just some. So we just move from we just jump from frequency to frequency and collect the number of the number of the states in phonon line width. So and that's why, as I told, that's why they coupled in such a way. So those and this function and phonon frequencies and phonon line widths. Yeah, but we need this line widths to calculate then phonon spectra, this spectral function. That's by integrating this spectral function. Maybe you remember then when we made our DOS calculations last term, there was some integral parameter. When we sum up all DOSes, we should get the number of electrons in the system. Here we made this integration of this function, so we sum up all the states, we get some frequency, and then it goes to this critical temperature.
Thank you.
I hope everything will be okay, because I spent really a lot of time to check all the bugs. Okay, we had to start with relaxation. I think it should be not a huge problem. Now I just we see. Now I had to. I just will show like lead. It's just like Plumbum. Yeah, we have this cubic lead. You see, it's only one atom, only one side in the unit cell. It is super simple, this structure. It's like cubic crystal system. That's why we use IBRAF 2 is cubic. Sodium 1 is just Bohr in Bohr units. This length 499. Then we have number of atoms 4, but if I use IBRAF 2, I can reduce it by the symmetry, and I will have only one atom in the 0, 0, 0 position, because all other atoms will be showed by applying the symmetry. That's why I have only one atom here, 0, 0, 0, and also some new things. I use ultra soft pseudo potential. Okay, I will start it because it will take some time. And then
there are two vertical slashes after control sequence. Won't it lead to any error? I hope it will not.
What slashes?
So after in the relaxation.
Yeah.
Yeah, there are two of them. I hope that this won't lead to any syntax error.
It just means like, yeah, it will not lead to any
okay.
To any errors. It's not like some thing. So here I use ultra soft pseudo potentials. They by using because this routine for electron-phonon calculations, it is not implemented for plane augmented wave pseudopotentials, which we used before. That's why I had to use this pseudopotential. And when we are using ultrasoft pseudopotentials, we had to increase electronic density. So you cut R rho, it's RHO, it means like rho, like density. We had to, by default, it's 4 multiplied by cut WFC. But here, if you use ultrasoft pseudopotentials, we should increase this density. That's why, and at least for 10, so maybe 8, 10, or 12. So I took 10. I took this multiplication factor of 10. Okay, and also I took smearing MV. It was in a Quantum Espresso example. I thought that I will not change it. The Gauss, you remember from last time that the Gauss is very important for some cases, for phonons especially. So I took it not so huge. So it was like, an example, it was like 0.005 or something like this. It was 10 times more, but I think it's better if it is smaller. Okay, let's see how our calculations going. It will take some time. You see, with so many we can discuss in this time. We can discuss SCF to F. So this is the same input as for SCF calculation. The main two differences here. Yeah, the thing is with this ultrasoft pseudopotential, convergence threshold also so huge, minus 12, and also I used it for relaxation because yeah, it will slightly improve our results in phonons. Here I took also this 18, 18, 18. This is what I call very dense mesh. But for normal SCF calculations, we will use smaller mesh just to make the calculations of phonons faster. Because with this 18, 18, 18, it will take considerably large amount of time. And the thing here is this LA to F true. It means that we allow these results to be stored in the file in the form which can then this routine for electron-phonon interactions read and use for further calculations. Yeah, it finished. What about your progress? And it finished with cell parameters. So this atom didn't change its position. It's ideal. And I have to take this cell DM1 and to go to the SCF.
Yeah, mine has also finished.
I will do it.
Mine is still running.
I think that it will finish in a few minutes.
Let's hope so.
Then I copy it to my SCF. Save it. And then I copy it to another SCF. Second SCF file is the same as first, except we don't have this line for spectral function, and we have the number of points not like 18, 18, 18, but just 9, 9, 9. In all other things, it is the same. It's just the step we need just to make our calculations faster. SCF A to F, launch it. And here we see this file. we see this file pb82f save. So we have just our common folder plum save, but also we have this spectral function save. So it's like slightly crazy, this file, but we don't need to read it. It will be readden by Electron-phonon part of calculation. So I'm going to SCF. I also launch this calculation. Don't forget to insert new LDM from relaxation. Job done, 8 seconds. Hope that everything went well. I hope that for SCF, so when I'm going to the next step, if some of you has just running calculations, you can say, and I will wait a bit. So next step, this Electron-phonon folder, Electron-phonon. We see here a lot of files. We see this ELF in, we see this lambda in, or maybe I will show it like this. ELF in file, boom, ELF in. It is, okay. Let's start the calculation maybe, and then we will discuss it because it will take some time. Here should be, okay, so you can just start QE script, and then we will discuss it.
You don't need to copy anything in this folder.
Yeah, it was mistake. Yeah, you see, it was my mistake, and I have crashed because fatal error in XML. Yeah, we had to copy. What we had to copy? We have to copy from this SCF, from pure SCF folder. We have to take this PB save folder. Copy. And we should take this XML. Then we should go to this folder and take this file as save. It will be used on Electron-phonon step. I will show you then this routine. Which use it. So from SCF folder and XML, from SCF A to F, we should take this file, A to F save. Yeah, and now I will start it and it will work. Yeah, it works perfectly. You see that we have this 4 Q points for mesh 333 because we have super high symmetry crystal only with 1 atom, and it will make the calculations for each Q point. But before we should be familiar with the files. First file, plumbum elf in, like elves and orcs. Elf in. It is almost the same file as phonon file. The common things like prefix, threshold, calculation threshold for this SCF cycles inside phonon calculations. Then what we have else, MS, this parameter disp. This is all these lines. They are common for phonon calculations from our previous labs and for this. So it's like Q mesh. But here we have something new. Okay, this is also common. Name of dynamical matrix for phonons. But here is something new. here we can store the derivative of the constant potential. It will be some folder for this derivative. From this derivative, the program takes this matrix elements for electron-phonons. So it is opens by this trans option and electron-phonon option. So electron-phonon option, it reads that A to F file which we copied to this folder. Then it reads this derivative of constant potential, and then it takes this electron-phonon and then it calculates this electron-phonon coefficients from the matrix. And also we have two other parameters, elf sigma and elf and sigma. So it's broadening or smearing. Because as I told, the smearing parameter is very important. So we try few smearing parameters here in one calculation, and then we had to choose maybe the parameter from which the results will not change a lot. We made it last time we made it on one of our previous laboratory works with phonon DOS. When we calculated phonon DOS with different smearing parameters, then we saw that with rather root parameters, it was like one result, and then all results they was very close to each other. And n sigma, it means the number of these broadening steps. So it's broadening step 0, 0, 5, and then it's a number. So it will be 0, 0, 5, 0, 0, 1, 0, 0, 15, and so on. All in Rydberg, of course. If I will go to this input, to this ph.x description, I can see electron-phonons that we have a lot of options. Yeah, we have interpolated. It is one of the most common things. So we take this brilliant zone, then we calculate in some dots in kipoids this electron-phonon coefficients, and then they are interpolated by some algorithms. Of course, we have tetrahedron method. It takes more researches, it takes more time, but it's plus that we don't need this. We don't need to make this broadening thing. I mean, for tetrahedron method, we shouldn't do all this stuff because it takes it in one shot. So it takes the best. So it takes the best assumption for our parameters for electron-phonon matrix, but it takes really a lot of researches to calculate, and some other things like anharmonic calculations. So I didn't use this. I used only interpolated and lambda tetra this parameters. Okay, what about the output? B11 out. So we have this file. Here is the same thing as it was for phonons, because we have this phonons and electron-phonon calculations in one calculation. Number of irreducible Q points. For 333, we have we should have 27 Q points, but thanks to symmetry, it was reduced to only 4. Each of these Q points will consist of modes. So we have only 3 modes. We have only one atom. That's why we have 3 modes. because we have 3 degrees of freedom and 3 modes, it means that we have only acoustic modes. So for one atom in unit cell, we have only acoustic modes, no optical modes. For first reducible representation, we have only for first Q point, we have only one representation with 3 modes, and it calculates with like self-consistent run of it's like 1, 2 in 4 iterations. So in 4 iterations, it was calculated with the 3 modes for gamma point. You see these frequencies of these phonons in gamma point, and then we have something new. Then we have this block with electron-phonon interactions. It takes that file which we can copy it from SCF, A to F save, and then it makes this broadening. So you see it takes broadening 005 Rydberg. This is what we mentioned here. So this, I mean this smearing step 005, then will be 01, 15, and so on. 01, 15, 20, 25. Then it calculates those density of states on Fermi level. Why we need density of states on Fermi level? Because they are here. You see, in this when we create spectral function and the Copeland constant, we have number of states at Fermi level here. So we calculate a number of states at Fermi level. Then we calculate, of course, this Fermi level. So for this 0 point, it's not so super interesting. You see that maybe some lambda, we get also this lambda coefficient and gamma coefficient. What means gamma coefficient and lambda? Lambda is obvious and gamma is this phonon line width. So for gamma point, phonon line width is almost 0. Then we move to another gamma to another Q. Then we have in this Q we will have 2 irreducible representations. One representation in 7 self-consistent steps. Then another representation in 4 steps. This Q stands for 8 points because it was, you see, they almost the same, but this orientation, this minus, plus, so it's all combinations of this of minuses in this matrix 3 on 8. Frequencies and also this electron-phonon interactions. Also we have this broadening things. Now we have some huge broadening for it, and we see how it changes. We see that for small broadening, we have rather huge coefficients. So we have rather huge phonon line widths, and then it decays, and from some point it almost don't change. So I think that it's like maybe this 5th point here. So and 158 and 141, and the difference is not so huge. But here the differences are huge, from 11 to 4, from 4 to 2, and so on. So maybe from the 5th step of this broadening, we get some reasonable results. Another key point. Yeah, for another key point, maybe I should renew it. Yeah, it finished. It took only 7 minutes. So for another point, the thing is the same. So we have we have 12 Q points in the start. So we reduce it to symmetry 12. Symmetry reduce it 12 to 1. We have these 3 representations, each representation for each model, and then we have it's also just to illustrate how it decays. So gamma, this phonon line wins, it was like 647. Then it goes like, I think from maybe this point, maybe this or this point, it stabilizes because now then it almost don't change. This is the thing with this broadening, because we don't know which broadening we should use. We don't know it from the start. Yeah, that's why we use the number of these broadening parameters to see at which point it will converge. It converges like maybe at this point, yeah, 002 Rydberg or 0025, because then it decays very, very slowly. Okay, I hope that all of us get the same result. Now we can go to another step. So in this step, we have calculated, phonon matrix and matrix for, you see, this is each this is a spectral function for each dot in this broadening. So like 51, 1, 2, 3, 4, and so on. And we have 4 lambdas. Each lambda for each Q point irreducible. Yeah, this is what this is what we discussed. So it's files with this broadening. But it's all in reciprocal space. Now we had to make this Q2R calculation. Where it is? Yes, this Q2R calculation. It is the same as calculation as Q2R for normal phonons, except this parameter. So it says to the program that it should take that results which we get from previous step and turn it from reciprocal. So it may apply Fourier transform to that results, and we can start. I just for some simplicity, I made the script elf pp because we have a lot of this post-processing steps, and that's why I didn't want to change hugely that script with ph.x. Here is also only one only one processor, and here we should change it to Q2R. Q2R. We will go then to lambda step when we will create this lambda. Q2R. Yeah, and the difference here is that I removed this npool4, which standard for key points, because it will not work with only one processor. Number of processors should be divided by number of this npool parameter. So we had changed here only this Q2R.x, and then we can launch it. LPP was post-processing, Electron-phonon post-processing. It will take just like 0.02 seconds. We can check is everything is okay. Yes, here Q2R. We see we see that everything is okay. So it took these key points, one key point reducible, then second, which stands for 8, 6, 12, and also something new. It takes this thing that preparing gamma for A to F for the spectral function. So it takes this broadening, then takes some number of points and move it to so apply Fourier fast Fourier transform. If T checks, it means it stands for fast Fourier transform. This is the only difference from Q to R for normal phonons. And now in our algorithm, so we successfully finished this step. Now we are going to this step. So we had to to calculate the dynamical matrix for phonon to get phonon dispersion. And then we had to get this electron-phonon broadening. So let's make this calculation. I will show you this PB matdyn in file. Here all is the same as for normal phonons, except these two things. I had to specify those fields because it's different kind of calculations, but I had to specify this spectral function true, just to apply this routine to our results. And also here is our path gamma x omega L. It's all from sig path. Calculate it. I have to change slightly my script elfpp, so matdyn.x. Yeah, that's the only one I had to change. It's just matdyn dynamical matrix. Then I launch it. You see, I will tell a few words about this inputs. This phonon spectrum electron-phonon stage, ph.x, these things are new for this electron-phonon routine. Yeah, and from this spectrum, we get these coefficients. So we have, you see those derivatives, yeah? PB, it's like plum. dv, it's like derivative from v, from constant derivative. Here it is, this constant derivative. Yeah, and it's like how Quantum Espresso works to calculate this matrix. It takes our constant potential, makes it derivative, then calculates it for different q and gets this matrix. So, but it will be in Q, in reciprocal, in Q space. So then by applying this transformation, we go to real space for this thing. And this step, so this matdyn step where we now, it will give us phonon frequencies at this path. And also it will give us files for phonon line widths, which will be used to calculate spectral function. Yeah, seems like we had to do a lot of steps to get something. So sup elf p is for matdyn. Okay, you had to make this q to r and then matdyn.
Yes, yes.
I'm doing this matdyn thing. And now what is here? A lot of files. Here we have few new files. We have dynamical matrix. So we have dynamical matrix for phonons. It's a typical thing from our last lab works. So dynamical matrix, these frequencies, and so on. But then we take like we have dynamical matrix for this spec, which will be used for electron-phonon calculations. Here it is. Maybe it's yeah. Here is this matrix. It's rather complicated. It is for each Q point in our path. So we have some paths, like 6 high symmetry Q points, between them 20 I mean this path here, between them 20 points in the lines. So it's like together 101. 100 because 1, 2, 3, 4, 5, 5 on 20, and this is 1. That's only 1. It doesn't matter how much points here because it's the last point, so it will be only 1. That's why we have like 101 Q points with this dynamical matrix for this Q point. And then we have all this see, we have this 10 files. Each file stands for broadening. Elf gamma 1 view, like K point or Q point, yeah. And for each model, we have this phonon broadening for each model. These files will be used then for next step. Our next step, so now we get these files, this gamma, this. So we got this phonon line with these gamma files, yeah. We also, and now I want to get lambda and I want to get spectral function. I had to do it with this 13. It's also matdyn. I called it matdyn A to F just to highlight that it's for spectral function. Here it is also almost the same as for phonon DOS. You see that if we create file for phonon DOS, it has this number of dots, but we also have just this additional thing, L to F, A to F, and it will take the files for spectral function. So we can slightly check the input. Here, just in the name, I just change the name A to F, and here A to F. The only thing I had to change. In file and out file. Executable is matdyn.x. It don't change. Then I launch it. It will also take like a few seconds. I'll just check, is everything okay? Yeah, everything is okay. Now we almost got it. So now we are almost at our finish.
Sorry, should I change the model name? The name of the model?
No. Model name matdyn.x.
Just the Just
Yeah,
the name of the file. Okay.
yeah, just name of the file. Because matdyn, we can calculate with matdyn this dispersion for phonons and line width. And we also can, with the same matdyn, with different parameters, we can calculate phonon dose and this function. What we got? I'll check, is everything okay? Yeah, everything is okay. Then what some interesting things we have? Let's write some matdyn matrices. We have phonon files, and now we will make plots of everything. So we have files for phonon. We have files for this spectral function for phonon dose, but we will not make them in this lab work. Then we have files for spectral function. These files for spectral functions are here. You see, A to F, DOS1, DOS2, DOS3, and so on. What's the difference? It's only the broadening. It's different broadening. The lowest broadening 1 and the highest broadening 10. And now we can make this plots. So we can make some plots. I'm going to the node Q sub minus E. Then I'm moving to my folder. It is lab 17 and ELF. Yeah, I just want to plot it. So I have this phonon script. It's just our common phonon script, but adopted for this system. Nothing special. I want to launch it with Python. In our seminar room, it's better because I see how you're working and I see your reactions. Now I don't know if you're on the same stage as me or not. So that's why I'm asking some from time to time. Wow, it's like super ugly. Yesterday I got something better. Why it is so ugly? Yes, I can show you the plot I got yesterday. Yeah, this was my yesterday's plot, and now it's like in the mem. Okay, yeah. Something. You also got such ugly plot.
Yes.
Something, I think that something went wrong at some point, maybe. Something went wrong. Yeah, maybe we had to use more cup points, like 999. Maybe it was not enough. Maybe yesterday I used like 18, 18, 18, and now I thought that maybe 999 will be better. That's why we got so we can work with even such. No, I think that it's still something not wrong. Something not wrong. Okay, let's see what will happen with A to F if this will be okay. I just wanted to show you this phonons dispersion just to illustrate that we can phonon dispersion. We can try to calculate to plot this DOS, and I want we have this script tb a2f. Yeah, I just took to compare three spectral functions. Yeah, Mikhailo, you didn't close your microphone. So I just wanted to show for three broadening, like for first broadening from the fifth, which I think is like the start of convergence, and the last one, and all other things. It's like it's like for DOS. So I even didn't change the names. So you see DOS values, like read DOS data and so on. So I even didn't change it. I just changed like frequency, Eliashberg spectral function labels, and this name. I want to launch it. Python. So it's almost the same script as we used for DOS, because files are the same. I will show you maybe this file. Just random. Here we see the first. This is like frequency. This is our spectral function or total dose, yeah, and its spectral function for each model. So I can, if I want, I can see how each model interacts with electrons, at what frequencies the biggest interactions. And now I want to launch it. It will be Bloomberg A2F. Hope they will be not so ugly. But now I'm not sure. Maybe it also will be super ugly. I had to find file, yeah, this PNG. Yeah, they are also not perfect, but better than photon dispersion. Here you see, we have frequency. Frequency in readers, we can calculate it in kilohertz if you want. This density of states for this Eliashberg spectral function is like, and we see that for the lowest broadening, 0.005 Rydberg, we have the biggest function, so the biggest number. And then when broadening goes up, so it's a reversible process. So when broadening goes up, it converges. This is unconvergent. So this is very root scheme. It's the same in the form. It is the same as this function, yeah, and as this, but it gives but it's like smearing, like it's smearing in some space. But then it starts to converge from I used here 5 step. It's like 0.025 Rydbergs, but maybe it starts to converge maybe from third, so something like this. Yeah, that it don't change with time. So this two, they don't change. So this is spectral function. This is our spectral function for electron-phonon interaction. We can say that at higher frequencies, we have the biggest interactions between electrons and phonons. We can calculate these frequencies. We can say that here. Generally, it has the same form as phonon DOS. If you remember that phonon DOS, it has here very, very low tail, and then it goes to something here. But here we have the same tail as for phonon DOS. Because here we almost don't have phonons. That's why we don't have phonon density of states. That's why we almost don't have any electron-phonon interactions. Now, we had to move further. We also have this file lambda. You see, in this file, we have this is also output from our last action. So we have this broadening in Rydberg's. We have this lambda parameter. Lambda parameter is this lambda parameter, yeah, for spectral function. Because we have spectral function, we have lambda. Strength of electron-phonon coupling. Then we have such amount of doses at Fermi level. So you see it stabilizes from maybe fourth and fifth step. It almost don't change. And lambda don't change, and this number of number of states. And then we have this omega. This omega is like integral omega for our formula. This is omega log. So we have lambda, we have omega, and what we need to do is just calculate this, just estimate this TC, this superconductive temperature. And we are going to last step. Last step is plumb lambda in. This is last step. So it's like, it's from Quantum Espresso example, so it has a lot of comments. Here a lot of such parameters. You stay here Emax, something more than highest phonon mode in terahertz, like 10. Okay, the highest phonon mode, it was like maybe 6 or 7, don't remember. The Gauss value for this calculation, and Smearing method. Smearing methods is like 1 stands for the Gauss. Number of Q points. Number of Q points, it was 4, yeah. And here we should specify Q points and their weights. What means weight? Weight, it means for how much Q points are in this Q point by the symmetry. So it's like for first steps 1, for second 8, 6, 12. Where we can take this information? We can take it from output of PB Q2R out, or from phonon calculations output. But here they are together. You see, first 1, for the second Q point, we have 8 Q points, for third 6, for fourth 12. Yeah, together 27. So this is just our Q points. Here is just path to where our lambda information, lambda output is. So ELF output file names in the same order as Q points before. So each broadening for each lambda. So what is it? ELF dir, ELF input lambda. ELF dir, here they are. Yeah, in these files, we have this information from ph.x output. So just lambda, gamma, and broadening parameters. So we just specify these parameters. And here is 0.1, this Coulomb coefficient for screening, for colon screening, this coefficient mu. We can write, it should be like between 0.05 to 0.15 or 0.16, something like this. I took 0.1. And we will use, and we will get as a result the TC. some estimation of superconducting temperature. So I can change the script. Now we have new module lambda. Module lambda stands for calculation of critical temperature. Lambda. Here and here. Yeah, got it. This is only one thing we should change, lambda. And now I count it. We are on the, I'm on the node, so I should exit. And now I can launch. What we'll get as a result, I hope everything worked well. As a result, in file lambda out, we should see
Yes, I got it. It's
you got
13 Kelvin.
it starts
for
from
the highest.
It
starts from 13, yes, and then goes down to 3.7.
lambda out. Here it is. Yeah. So we see this just this stuff. So lambda information, this constant for electron-phonon coupling. So the higher coupling we have, number of density of states on Fermi level, this broadening, and this omega, which we used in Macmillan formula for TC. And now here lambda, finally lambda, omega, TC. And you see that, so we agreed that it should converge from like fifth or fourth step. Yeah, because before the steps, the difference will be so huge. So we can take like 1, 2, 3, 4. So maybe from this or this step, we should consider our TC. So it's like between 5 Kelvin and 3 Kelvin, like almost 4 Kelvin. The literature, like for Bloom.
7.2.
Sure, yeah, 7.2. Yeah, so maybe we should take even a third step. It's not converges so ideally, I think, but it also has it in range. But you see, it's like estimation. It's rather good estimation because we didn't get like 200 kelvins. We got like in this model with this accuracy which we use, with this theory, with this semi-empirical formula for TC, because we have this Coulomb screening potential, we can get this from almost 4 Kelvin to 13 Kelvin. And now I want to change mu. Let's see what will happen if I will change mu. PB, lambda in. I can change mu here, for example, for 15. What will happen? It's empirical parameter, so we can get it. I don't know, even from here. If it's possible to take it from the experiment. Soup. And then
TC obviously became lower.
Yeah, we increased the screen, the Coulomb screen, and TC goes down. Yeah, and if we will make it lower, like 0.5, we can also check it. Yeah, it goes up. So when we change, yeah, it's obvious because we have it here in this exponent in the bottom. So perhaps 0.05, 0.1 are okay for these calculations, because you see, because here we get like almost 7, so like 6.8. Before it was like 7 something. Yeah, so we get rather good estimation of TC, but of course it's not like ideal matching. Yeah, because for experiment it can be rather rather important if it's 7.2 or 7.0 for some experiments. So we can't in this level of theory, in this level of accuracy, we can't have so huge accuracy. But we can I can give you as another part of model homework to reproduce these calculations, but with higher accuracy, with higher number of key points and so on, and to see if we will get normal phonons, and to play with this parameter of screen, to play to see how we can change this TC. So if we can converge it to 7.2. So if we will increase parameters, it will take, of course, more time than 7 minutes. 7 minutes is for seminar. So if we can get like, I don't know, 6.5 and 7 point, is a range from 6.5 to 7.5, something like this, not from like 5 and 14. Yeah. For today, it's all what I wanted to tell you. I think maybe it's rather hard from one time to get all of this, because it's really, you see, we have some empirical parameters. Yeah, we don't know it. We should change it in some way. Yeah, we have a lot of new stuff. But I tried to show you the differences between phonons, which we can do. So these differences, so like these differences, and maybe in input the difference is not so huge as it may seem when you compare it to phonons, of course. So maybe you have some questions.
Yeah, we saw that now it was an underestimation of the TC if compared to the experiment. Is it like a general rule of thumb that it usually underestimates rather than overestimates the TC?
I don't know.
Or it's just
I don't know if it's a usual rule. Maybe if we can try it for tetrahedron method, tetrahedron method should give us like only one number, not like range of TC, but only one TC. It's interesting to see what will happen if we use tetrahedron. Maybe I will make these calculations. In tetrahedron method, you should change not like here gamma tetrahedra or lambda tetrahedra. You should also change here tetrahedron methods. Make this non-self-consistent calculations with tetrahedra, because we can't make self-consistent with tetrahedra, and so on. So we should make like considerably change here, but we will get one number. It's interesting what will happen here.
I have one more question. Sorry.
No, I will finish. I think that if we will increase the accuracy of our calculation, this range will shrink, so we will have lower range.
Okay, yeah, that's reasonable. One more question is that, so here in this method, we actually compute the two-particle spectral function for the electron-phonon interaction. But there are some systems with strong electron correlations, where we might need to have two-particle spectral function for electron-electron interactions. Are there some modules in Quantum Espresso that allows to do that?
You mean to combine U plus these things?
Well, no, not really. I mean, I thought. Well, never mind. I just it's hard to explain.
Electron interactions are in our quantum potential. It's like it's Hartree energy. If we have relativity system like huge atoms, we can have I don't know. We should to apply the screen parameter U parameter.
This I know.
For phonons should be so I think that we can come. I'm not sure because I didn't calculate phonons with U. I think they should be connected because U is very popular method. So
yeah, I see. Well, it was you. We're still saying the one particle.
Yeah, it's still one particle because you see, maybe you mean some GW or something like this for
yes, something like this. Yes.
I don't know. So Quantum Espresso has GW module, but I don't know if it connected to phonon 6 things because DFT is by default is one particle because we have one particle and which interacts with mean field, the self-constituent.
Yes.
We have mean field and one particle. It's not like have two particles, yeah, which interacted with each other and with.
Okay,
I don't know. So maybe some more questions. If not, so thank you a lot for your attention. I don't know if it was okay in this format. For me, it was worse because it's better to be in ZAO to see you, but it's only for one time. So thanks and bye for next time.
Thank you for the lecture.
Thank you.
Bye.